Have you ever wondered how a self-driving car decides in a split second when to change lanes? Or how a trading algorithm knows the perfect moment to buy or sell a stock? Well, it all comes down to a really powerful framework for making smart choices when you just can't predict the future. And today, we're going to break down exactly how it works. So here's how we're going to tackle this. First, we'll get a handle on the basic problem, making decisions when things are messy. Then, we'll build the framework they use to solve it piece by piece. We'll get into the brilliant idea called the principle of optimality, see how the algorithms actually find the best move, and then we'll bring it all back to the real world. All right, let's dive right in with Section 1, the decision-making dilemma. Before we can even talk about the solution, we have to really appreciate the problem we're trying to solve. This is it. This is the big question. It's at the heart of so much in AI and economics. Heck, even in our own lives, right? Every choice you make today opens some doors and closes others for tomorrow. But the tricky part is, you never know exactly what tomorrow is going to look like. Okay, let's make this concrete. Picture a small store. If the owner orders way too much stuff, they have to pay to store it all. That's money down the drain. We call those holding costs. But if they don't order enough, they run out and they miss out on sales. Those are stock-out costs. Finding that perfect sweet spot is super hard because you never know for sure how many customers will walk through the door tomorrow. So to solve a puzzle like this, you can't just wing it. You need a formal language, a way to describe the problem precisely. And that's exactly what a Markov decision process, or MDP, is. It gives us a structure with 4 key ingredients. First up, we've got the state. You can just think of this as a snapshot of right now. Where are we? What's the situation? For our store owner, the state is just the number of items on the shelf. For a little robot cleaner, its state is its exact position in the room. Easy enough. Next, from any state, we have a menu of possible actions we can take. The robot can move left, right, forward, or back. The store manager can decide to order 5 more units, 10 more, or maybe none at all. These are our available moves. But here's where it gets interesting. The world is uncertain. If the robot decides to move left, will it for sure end up 1 square to the left? What if the floor is a little slippery and it overshoots? The transition probability is what captures this randomness. It tells us the odds of landing in different future states for every action we take. And finally, how do we know if we're doing a good job? We get a reward. It's feedback. Selling an item gives us a positive reward, profit. Paying to store extra inventory, that's a negative reward, a cost. And the goal isn't just to get the biggest reward right now, it's to make choices that give us the most total reward over the long haul. And this diagram here shows how it all fits together in this beautiful continuous loop. Our decision maker, we call it the agent, looks at the current state, it takes an action, the world or the environment, then gives back a new state and a reward. And then the whole cycle just starts all over again. Observe, act, reward, repeat. Now, there's a really important assumption here that makes this whole thing solvable. It's called the Markov property. And all it really says is that the future only depends on the present. We don't need to know the entire history of every single move we made to get here. All the useful information for making the next best decision is already baked into our current state. This one idea is what keeps the problem manageable. Okay, so we've laid out the problem, but how do we actually find the best path forward? Well, that brings us to this flash of genius from a mathematician named Richard Bellman. So this is Bellman's principle of optimality. I know, it sounds a little dense, but the idea is actually super intuitive. It just means that if you have the perfect route planned from New York to Los Angeles, then the part of your route from, say, Chicago to Los Angeles must also be the perfect route for that shorter trip. It lets us break a giant, scary problem down into a series of smaller, bite-sized ones. To actually use this idea, we need something called a value function. Imagine you could put a score on every single state, every possible situation that represents how good it is to be there. Not just for the immediate reward, but for all the potential rewards you could get from that point forward. A state that's just 1 step away from a big win would have a really high value. So how do we find those scores? That's where the Bellman equation comes in. It's the secret sauce. It basically says the value of where you are right now is the immediate reward you get, plus the value of the best possible place you can get to next. It's recursive, meaning it creates this chain reaction that links the value of the far future all the way back to the decision you need to make right now. Okay, now look closely here, because the difference is subtle but incredibly powerful. The equation on the left just tells you how good a plan you already have is. But the one on the right, the optimality equation, it has that little max operator in there. That one addition tells the agent, hey, don't just follow the plan. Look at all your possible moves and pick the one that leads to the absolute maximum future value. That's the leap from being good to being perfect.
So we have this amazing equation. Now, in section 4, let's look at how we actually put it into practice with a couple of classic algorithms.
So it's a really elegant equation, for sure. But how do we, solve it? How do we use it to actually calculate that perfect value for every single state, which then tells us the perfect action to take no matter where we are? Well, the two classic methods are value iteration and policy iteration. You can think of value iteration as just hammering away at the values over and over again, refining its guesses until the numbers stop changing. Policy iteration is more like a two-step dance. First, it figures out how good its current strategy is, then it makes that strategy better. It usually takes fewer big steps, but each one of those steps is a little more computationally expensive. And this is not just some academic exercise. This framework is the engine humming away behind some of the most impressive AI you see out there today. Seriously, the applications are everywhere, and they're growing every day. This is the logic that helps a robot navigate a chaotic warehouse. It's what optimizes huge stock portfolios, and it's a core piece of how self-driving cars make decisions. It's even being used in healthcare to design better treatment plans and, to solve that same inventory problem we started with. All right, so if you're going to take away 3 things, let it be these. 1. MDPs give us a formal language to talk about making decisions when we're not sure what's going to happen. 2. The Bellman equation is the genius, recursive tool that lets us connect the future back to the present. And 3, putting it all together lets an agent find the best possible strategy to get the most reward in the long run. And this all leaves us with a final, really big thought to chew on. This technology is incredible at finding the most efficient, optimal path to a goal. But as we apply it to more and more parts of our lives, our money, our health, our jobs, it begs the question, what decisions are uniquely human? Which choices should we always keep for ourselves?